100% performance score in AI is often seen as the ultimate goal, but this view is misleading. An AI model that achieves perfection on its training data can, in reality, fail completely when faced with new information. This makes a perfect score less of a success and more of a warning sign of a fundamental problem.
Imagine a machine learning model is given a specific set of data to learn from. After a while, it achieves a perfect 100% score on that exact data. Every single answer is correct. At first glance, this seems ideal. You'd think the model has completely mastered the material. But in the world of machine learning, this is actually a classic sign that something has gone very wrong.
Here's the problem. That same model, the one that was flawless on its training data, can be totally useless when it sees new, unfamiliar information. It has a perfect memory of the past, but it can't predict the future. And this gets to the very heart of the generalization problem.
This type of failure has a name: overfitting. It's what happens when a model doesn't learn the general principles from the data. Instead, it just memorizes the training examples, including all their random quirks and irrelevant details, what we call noise.
Think of it like a student preparing for a big test. If they just memorize the answers on the practice exam word for word, they'll ace that specific test. But when the final exam comes around with new questions, they'll be completely stuck. They memorize the answers, but they never actually learned the subject.
The reason this happens comes down to a core principle in machine learning, what's known as the bias-variance trade-off. And this is a constant balancing act.
On one side of this trade-off, you have bias. Bias is the error you get when a model is just too simple. It makes these big, overly general assumptions, and because of that, it completely misses the more complex patterns in the data. This is also known as underfitting.
A high-bias model is like a student who learns one simple math rule, let's say addition, and then tries to solve every single problem with it, even a complex calculus equation. The tool is just far too simple for the job.
Now, on the other side of the trade-off, you have variance. This is the error from a model being too complex, too sensitive. It pays so much attention to the training data that it doesn't just learn the important patterns, it also learns all the random, meaningless noise. And this is overfitting.
And this brings us back to our student analogy. A high-variance model is like a student who memorizes their textbook so perfectly that they can even reproduce the typos. They've learned the material, sure, but they've also memorized the noise right along with it, without ever learning to tell the difference.
So you can see the trade-off here. As you make a model more complex, its bias usually goes down, which is good. It can learn more detailed patterns. But at the same time, its variance goes up, and that increases the risk of overfitting. The real challenge is finding the right balance between the two. But here's where it gets interesting. This classic bias-variance trade-off doesn't actually explain everything. Researchers have discovered a strange phenomenon that seems to completely break this rule.
You can have a model that looks like a complete failure. It gets 100% accuracy on its training data, but when you give it new data it's never seen before, its performance is terrible, basically just random guessing. It looks hopelessly overfit.
According to the traditional trade-off, this model should be a lost cause. You just start over. But researchers found that if you just keep training it for a very long time, even when it looks like nothing is improving, something totally unexpected can happen.
All of a sudden, the model's performance on the new data skyrockets from basically random to almost perfect. The model makes this incredible shift from just memorizing things to actually generalizing.
This phenomenon is called grokking. It's this moment of delayed generalization, where a model suddenly snaps from a strategy of pure memorization to finding a much more elegant, general solution that actually works.
Now, this whole challenge with generalization isn't just about models that predict things. It shows up in a totally different way for AI models that are designed to be creative.
You see, the goals are different. For a predictive model, the main thing you care about is accuracy. But for a generative model, one that creates things like images or text, there's another equally critical goal: diversity. A very common failure for these creative models is something called mode collapse. This is what happens when the model discovers one or a few outputs that work really well, and then it just gets stuck, producing them over and over again. It completely ignores all the other diverse examples it was trained on. It's a bit like a super talented artist who can paint one single, absolutely perfect masterpiece. But that's it. That's all they can do. If you ask them to paint anything else, they just give you the same image again. They've perfected one mode, but they've completely failed to learn the variety that makes up art itself.
So whether we're talking about overfitting, this strange phenomenon of grokking, or mode collapse, they might seem different, but they're all pointing to the very same fundamental challenge in AI.
And that challenge is this. The real goal of an AI model isn't to perfectly memorize the past. It's not supposed to be a perfect archive of data it's already seen. After all, a simple database could do that job. The model's true job is to learn the real, underlying patterns in the data, to separate the important signal from the random noise. The quote here says it perfectly. Overfitting is when the model accidentally treats that random noise as if it's a meaningful part of the actual structure.
And this explains why our initial intuition is so often wrong. It explains why that perfect score can be such a red flag. A model's true performance isn't measured on how well it remembers the data it has already seen. It's measured on how well it can generalize from that past to a future it has not yet encountered.